So hello everyone, this is Swarup, Assistant Professor, Mechanical Department. So the subject design of machine elements 2. So today we'll be learning few on bearings. This is lecture 7. Okay, data handbook is 4th edition, the Belgrade ready. So this is the basic chart which you have to remember. Okay, to proceed further to get the data for the bearings. Okay, with respect to the machineries which we will be given in the question. Okay. Okay. If the diameter is known, in the previous class we have solved the problems where the diameters are unknown. Okay. So today we shall solve when the diameters are known. Okay. The design is general bearing with centrifugal pump at 200 RPM. Diameter of the journal is 100 mm. Okay. And load on the bearing is 15 kilonewton. Now take L by D as 1.5, bearing temperature 50 and ambient temperature 30. So we have given the bearing temperature. Okay, find whether artificial cooling is required or not. Okay, now let's start. Application he has given is centrifugal pump. So in the previous one I have shown you the page, okay, where the tabular column signifies the application point of view, where the data of the bearings are being given, that is N is given in the question, D, L by D, L, okay, TB and TA, W. The parameters for the centrifugal pump. Okay, from that table you have to note down with respect to the centrifugal pump, which is at the last, okay, row. Now P max, C by R, Z, L by D, Z N by P. You have to note down the values. Now let us take the maximum pressure will be the 1.4 megapascal, that is from here. Similarly, L by L is equals to 1.5 D. D is given. L you can directly calculate it from formula. Now to find P, okay, pressure, that is W by L into D. Now if you substitute, you are getting the 1 megapascal. Now this pressure must be less than the maximum pressure, that is 1.4 megapascal. So then only L by D are safe. Okay. Similarly, next is to find the value type of oil. We have to find it out. So before that you have to find the kinematic viscosity in terms of centristrokes, and you can compare it with the graph to find the value of required curve, and you can compare it with the table of 15.1. This is the number of curve, and you can check the oil characteristics. Okay, so let's start. So we know from the Z, okay, which is being taken from the step A from the data table. Okay, now we know the temperature. Okay, here the temperature is TB minus TA, that is T naught. Okay, to find the value of curve, okay, we need the operating temperature. Okay, so what he has given in the question is the bearing temperature. So this step is very much important. I will repeat it once again. So bearing temperature he has given, ambient temperature he has given. Okay, so TB minus TA is equals to T naught minus TA by 2. Okay, we need the operating temperature. So, okay, so this oil temperature is required to find the values of required curve from the graph. Okay, so let's see further, you will understand it. Assume rho is equals to 0.9. Okay, since we don't know the curve, we cannot assume it, hence we are directly assuming it as 0.9. Okay, otherwise we have to use this formulas to find the value of rho t, because we don't know the rho 15, because we don't know the type of curve, hence we are assuming it as a rho as 0.9. Okay, now if you substitute back here, you will get the value of Zk, and Zk you would convert into kinematic viscosity in terms of centristrokes. Okay, so once you get the value of centristrokes with respect to the temperature of the operating oil, okay, you have to find the value of E. So if you check from the figure 15.3352, y-axis is 27.78, and according from the top, if you check the temperature, so if you meet at a particular curve, so that curve represents the E. Okay, so now if you check from this table, E is SAE 20. Okay, this is the type of oil. Next, bearing modulus Zn by P. If you substitute the values of Zn and P, you will get the value of C, that is 30. But from the table we know that Zn by P, that is minimum value, is 29.01, but minimum value of C at which film breaks is 3 times the calculated value. So hence divide this by 3. Okay, so this value where you got calculated C as 30 must be greater than this divided value. Okay, hence you can operate under hydrodynamic lubrication. Next step is to calculate Sommerfeld number. Okay, you know the value of R by C is Zn by P. Okay, if you substitute back, you will get the value of Sommerfeld number in terms of second per minute. Next, coefficient of friction according to Mecky's equation. Okay, this is the Mecky's equation, you need to use it here. We know that L by D lies in between this 0.7 to 0.2.8, or you can check it from figure 15.5b also. Okay, there delta F is equals to 0.002. Okay, now next Ka is equals to 0.195 into 10 raised to 6 for full bearing, that is beta is equals to 360 degree. Okay, if substitute back these all unknown parameters in this above equation to find the value of coefficient of friction, that is F. Second is minimum film thickness. Okay, so if you go to page number 356, that is figure 15.9. okay, in that figure with respect to S, that is 17.75 and beta is equal to 360 degree. If you cross check these two, towards the left side if you check, there you will be getting MFT. MFT means minimum film thickness is equals to H0 by C. Okay, that value is 0.94. If you multiply it with C, okay, so 0.94 into C by R. Okay, we will be getting the value of minimum film thickness as 0.0611 mm. Okay, the next step is to calculate heat generated, that is Hg is equals to FWV. Okay, this you will be getting from the data handbook. Okay, now we need to find the value of V, that is pi dn by 1000. Okay, V is equals to 6.28 meter per second. Now substitute back in this Hg, F, W and V, you will be getting the value of heat generated, that is 895 watts. Okay, next step is to calculate the heat dissipation value. So this formula also will be getting from the data handbook, where dV minus T are directly given in the question. You can directly substitute the back for the bearing temperature and ambient temperature. Okay, so Kp, you know how to calculate, he has given in the question directly from the data handbook. Sorry. So if you substitute back in this equation, you will be getting the value of heat dissipation. So now it's time to check whether artificial cooling is required for this bearing or not. Since heat generation is greater than the heat dissipation, okay, hence if you take the difference of these two, you will be getting the required amount, where 849.33 watts is the total amount of artificial cooling which is required. Okay, which is required for the bearing. Completes the design problem of bearings. Okay, thank you guys.